Yeah, I was.
So here's the plan, for today. But I don't know how much I want to. I don't want to. I burdened you with the extra classes and so on. So let's see. I want to maybe go for an hour or so and then end. So I want to do a quick recap of. So we were talking about fixed point characterization. Okay, which kind of fixed point characterization really involves. Defining model checking. Now we are talking about CTL model checking as using functions that manipulate sets of states, that is predicates. Okay, so viewing them as giving CTL operators and their model, the characterization as fixed points of some predicate transformers is useful. Then what you have is, once you express them as fixed points of predicate transformers, that is, functions that map predicates to predicates, set of states to set of states, then an algorithm immediately falls out. Using this Kleene-Tarski theorem, a statement of which I also made last time. Time permitting, I may get back into the theory of fixed points and a proof of Kleene theorem later on. Okay, so then what happens is this gives the fixed point characterization will give a very general framework in which once you express these CTL operators, you can use Kleene iteration to get an algorithm, a symbolic model checking algorithm for model checking CTL formulas. And you can extend that to LTL as well. Okay. Then I want to do some quick notes on BDD implementation of this fixed point computation. So you can get started with your programming assignment, which is the crux of your assignment 2. And I also want to get into then I'll talk about some fixed point characterization can look a bit mysterious, okay, for you at times, and therefore you need some way of convincing yourself through a formal proof that the fixed point characterization of CTL formulas, CTL, the model checking, is equivalent to their definition that you have seen as semantics, that the way that we define formal semantics of CTL. Okay, that is how we have been understanding CTL formulas so far, as interpretations given to these logical formulas. So, but symbolic model checking can be viewed as fixed point computations. When you do compute them as fixed points of certain functions, you need to be convinced that it corresponds to the same thing, and that is something that I'll see. Then counterexample generation. Okay, so model checking, an important component is counterexample. To generate counterexample, even there, once again, those techniques can be viewed as, in some cases, computing some fixed point. Okay, so and then extension of this fixed point characterization of CTL model checking for doing model checking under fairness. Okay. Yeah. So, last time I expressed everything, the the way to compute fixed points, the fixed points themselves were fixed points of certain predicate transformers. The predicate transformers were expressed in terms of the EX and AX operators, the one-step operator, okay? And the predicate transformer corresponding to the CTL operators were defined in terms of EX and AX. And clean iteration was involved in computing the fixed points by iterating over using EX and AX. Okay, so, but I will want to show you, like in a picture. Sometimes this is, maybe hard to understand. I don't know if the picture will help you, or not. So here is EX of P, AX of P, an image. Okay, I started with image because I used the reachability analysis for this. So image is, all of them can be expressed in terms as existential quantification elimination. Okay, so the connection to BDD, it becomes very clear when you see as a way to implement these operations. Here I'm viewing each of them as a function which takes a formula, a propositional formula, and returns another, actually a pair of formulas. EX, the proposition formula, the subformula P, and of course, the meaning of EX is in terms of the transition relation. So those are the two formulas, and then it, this is exactly how EX of P is defined. Okay, that is, this formula on the right side defines the set of states that are denoted by EX of P. Since the transition relation is implicit in EX, you can say that it is parameterized. That's why the formula will also have the transition relation. Okay, with the image. Okay, let me start with image. Image computes the image of a set of states denoted by a formula A. Okay, and that is what is shown here. To start with some A, it is the image of A is, this is the existential, that I'm saying. So there exists, it is all those things that it is a set of all, successors of A. Whereas EX and AX, they do it backwards. Okay, so in that sense, they can be considered as pre-image. And look at this. So if you're given a predicate, so what EX denotes is the set of all states that from which in one step there exists a successor that gets you into a state that satisfies P. Okay, that's why it's like I call it as a pre-image. So the difference is in which variable that you quantify out. So AX of P is all those states whose every successor of which get mapped into P. So for example, this state will not be there in AX of P, okay, because it is. Is this correct? Yeah, I think. Yeah, because there is a state, there is a successor that it does not get you into P, and that's why this state will not be part of AX of P. Okay, so that's why this is existential pre-image of some predicate P. This is universal pre-image of P. Okay, so is this clear? Any questions here? And now I hope you can see how, if you assume that your transition relation and your formula P here, or in the image case A, they are represented as BDDs. You can view these, what I've shown here, as performing appropriate BDD operations. For example, this one involves performing an existentially existential quantification elimination over the conjunction of these two formulas. You can easily implement them using one of the functions in in BDD. That would be your starting point, okay, for using these fixed point characterization to implement your CTL model checking. So now, are there any questions here? Any questions? Okay. Now I'll move to, yeah. So this is what I had started with. So I don't know if you, I know Amin and you and Ratnakar were not there. I don't know if you had a chance to listen to my previous lecture. Did you?
Yeah, I did watch the recording.
Okay, so I guess this space is okay. Huh? So you understood what? See, this is so when we say we will be characterizing each CTL operator as in terms of fixed points. What I mean is we will define a function which maps predicates, sets of states to set of states, and the that particular operator, in this case EU is what I'm showing, will be defined as a fixed point, is the least fixed point of that function, okay, over predicates. So, I mean, then it boils down to constructing appropriate definition for the tau, okay. And once you do that, this is pretty much the same algorithm that I have here, that I've shown here, which iterates over these tau, okay, to compute the least fixed point. Okay, what I've shown on the right side is just a pictorial view of what this cleaning, what I call as clean iteration, is exactly what this program is doing. Okay, it is computing a chain of tau starting with false. Tau 0 is false. Tau 1 is application of tau, which I've shown here, to false, and tau 2 is tau 1, tau of tau 1, and so on. Okay. But what is happening is the way that this thing is defined, it starts with F2. Okay, it's it starts with as a second step. Okay, it starts with actually false. When you plug in false here, what you get is F2 as tau 1, and to that, each time you're adding actually the all those states that have a successor, a one-step successor into that satisfy F1, and also have a one-step successor into F2. Okay, and that's what is happening, and you keep repeating this until you reach a fixed point. You're only adding those states which satisfy F1, that in one or more step, okay, that you have a successor state that get into F2, okay, and that is what is happening with tau. So when so states like these that I've shown here, although they are inside F1, they do not have any successor going into F2 in one or more steps. Those things will not get added. Okay, so and that's what so you see, in one step you have a characterization of the CTL operator. When I say there's a characterization, what I mean is the set of states defined as per the CTL semantics is exactly equivalent to the limit of the tau chain that I apply to via the clean iteration that I compute. Okay, and that's what is happening here. So, any questions here? Okay. Yeah, similarly, F1 until F2, can be computed as a fixed point of this predicate transformer, where all I've done is replace EX with AX. Okay. So here, yeah, I mean, you will add those states only if every successor of that state, of the F1 state, goes in one or more steps into T. So the one or more step is coming from repeated application of tau. In each step, this one concentric circle is what is added to the what eventually becomes your fixed point. Okay. Now, yeah. So there's this question of how do you prove? Okay. So when I say it's mysterious, I mean we are computing it as a fixed point of this thing. Okay. So, I mean, intuitively, you kind of understand why why this the set of states that are included in the fixed point are exactly those set of states that that satisfy this CTL formula on the left side. How do you prove it is a question. So that we will get to at the end of this class in formula. On one side, you have you are computing as a limit of a tau chain. Okay. On the other side, you are giving an interpretation to the logical formula. Those two is what you will have to reconcile with each other. Okay, I will get to that. So now the G versions. I mean, for example, the EG, AG, can of course be defined as negation of these things in this case, but sometimes it is useful to calculate them as greatest fixed points as well, and that's what is I showed here. So when you so here you're computing it as the fixed point as the greatest fixed point of a descending tau chain, starting with with true. Okay. And when you reach the so you are in this process is like you are starting with true, which includes every state in the universe, and then in each step you are removing some states that violate some constraint that you are expressing as your that is being defined as your tau. Okay. So yeah. So for example, here, so you remember that. So here, what you yeah. So the best way to view this the greatest fixed point computation is to view them as in each step you're removing something that should not be part of your fixed point. And you recall how in the explicit state model checking EG, I mean EG was calculated. We started with the strongly connected components. Every state of which maximal strongly connected component, every state of which satisfied F. Okay. Now you see, it is kind of hard to start with that in your symbolic computation, because I mean, if you had the entire graph, you could enumerate the strongly connected component. But here, the reason you were able to use forward fixed point computation in terms of least fixed point for the until operator, EU operator, was because you could start with F2, okay, for which you had a symbolic representation. Whereas here, you don't have a symbolic representation for the strongly connected components. But what is the trick that you're doing is every strongly connected component and something which is a state which has a chain, that leads ends up on a strongly connected component. Something is a closure. Okay, I mean, strongly connected component is actually a closure. And if you look at that, what happens is in each step I'm applying this EF of EX of Z. Okay, so if you look at that, I mean, what is the these strongly connected components are exactly those that satisfy f and ex of f. Okay. And the kinds of states that do not belong to EG of f are those that do not have even a single successor into such a strongly connected component, like these states. Okay, so you can look at this state. It's an F state, but it does not, in one step, it leads to something which which is outside of which is outside of F. Okay, that is the one that you will have to remove. And the way that you end up removing is, and then that's what you do in your cleaning iteration. In each step, you are eliminating things that are violating this constraint of Ex of Z. So tau 1 gets rid of all the states that do not have any successor into, all the successors of which are leading to outside, like this. And tau 2 will get rid of from your existing set things that in 2 steps lead to this something that will not, that will lead you outside. Every successor leads you outside into a normative state. And when you reach the fixed point, all you're left with are these strongly connected components, which have every state of which satisfy F. Because if you look at a strongly connected component strictly, is every state in this kind of a loop satisfies F and Ex of F. Okay, and all these other things, these tails that you see here, are those states that are not part of SCC, but are a lead in one or more steps into a state which is on an SCC. Okay, so when you reach the fixed point, those are the only set of states that are left in your fixed point. Okay, so when you want to define a suitable tau, to represent your formula, to represent the set of states of your formula as something, as a fixed point of that tau, as a greatest fixed point, this is how you will have to view them. Okay, so here you yes, yeah.
Could you repeat that part about the connection with strongly connected components? I didn't catch that.
Yeah, a strongly connected component. If you look at F and Ex of F, consider that formula, F and Ex of F. What does it say? It says it includes those states which satisfy F, and it should have a successor. There exists a successor of that which has to satisfy F as well. Okay, so that one is certainly true of every state, every state inside a strongly connected component, every state of it satisfies it. Because if you look at that, look at the self loop. It's inside F, it satisfies F, and there is a Ex of F is also true of that. Similarly, this strongly connected component with 2 states, strongly connected component with 3 states, that all of them satisfy F and Ex of F. Okay? And these states that in one or more step land on a strongly connected component, they also satisfy F and Ex of F. Okay?
Oh.
That is the relationship. Why am I giving? Visually, that's what EG of F should have. Okay, EG of F should have. EGF should not have any state that has no successor, okay, in one or more steps into something, that satisfies f and ex of f. And that's what you're getting rid of, okay, in each iteration, okay. In each iteration of tau, that's what you're getting rid of. So here, you are keeping inside f, you're keeping those that you're starting with f, okay, and you're keeping those that have in one step. In each step, you're taking that in one step. It should, leads to something there. I mean, or the negation of it. Okay, you're eliminating those that does not have even one successor in those many steps. That is leading to, into something in itself. Okay, so is that
yeah, got it.
yeah, okay, so yes, so each tau I eliminates something that is leading to such things. These are clearly violated. This one in one step leads to something, everything in a success. So therefore that it should not be there, and that's what you're eliminating. Okay? And eventually, when you reach the fixed point, you only have these things here. Yeah. So in order to understand, let me see if I do time this. Yes. Yes. Okay. So I'll get to something. So you will have to, I think, you need some practice, some things to, I mean, I've been saying this can be used as model checking. Actually, fixed point characterization is only characterize the set of states, okay, defined by this thing. Of course, once you compute the set of states, it should be obvious to you how you can use that to do model checking, correct? In a Kripke model. All you have to do is, take your initial state and see if that is included in that thing. That's why I'm kind of abusing my language, abusing the language by saying this is also model checking. CTL model checking is also can be considered as characterization of, as fixed point characterization. Okay. Yeah. So as an exercise, we already. Yeah, so what do you think this one? I mean, this tau that I showed here. See, as you can see, when a tau, okay, Kleene iteration computes a fixed point only when tau is monotonic, which means the tau is monotonic if it either, given a z, it adds something to it, okay, in each step, or given a z, it has to take away something. Okay? So these functions which either have, which take away, when you're taking conjunction, you're taking away something. When you're in each step, you're adding a conjunction to your previous thing, symbolically. Okay? So they are meant to be used as, for characterizing, for characterizing what you want to characterize as greatest fixed point. So here, as you can see, is something where you add, if at all, something. Okay. Now, just stated this way, I mean, you will have to learn to kind of visualize and understand. I mean, simulate a few steps. I mean, there are two ways. Okay, one, given a tau, you have to try and understand what is the fixed point that a tau chain involving that tau computes. And then, given a CTL formula or some model checking task, what is it? How do you express it as a tau? Because once you do it, then you have an implementation using Kleene iteration pops out. Okay, so it is a very nice way to not to get an implementation. Okay, so whose correctness can be easily established. Okay, so now I'll ask the question: what do you think? What am I doing here?
Is it the set of states that are reachable from initial states?
Well, you know, if I just keep on adding, if I only do this, which is what reachable set did, I add image Z. Okay, if you notice, this is just a slight modification to it. It's a slight variant of it. If I were doing I or image of Z, what you said is exactly right. And that's exactly the tau that was used. Okay. But here, what I'm saying is I only do it as long as I don't see, I stop the moment that I see some image, some state in the image that I've already seen. Okay. If this is true, actually I should say this is satisfiable. Okay. Let's suppose this I say is, yeah, this is true, which means it is satisfiable. Okay. Then I stop there. So I claim this one is indeed accumulated, but it stops at the point where it lassos. Okay. So, you know, for that lasso, yes, it does. Okay. It computes kind of the shortest lasso. That's what I'm claiming. Okay. So simulate and then you know, try and think. So you will have to first express this. So the moment image of Z. Okay. I mean, when I compute in the ith step, some you know, so I start with I, some initial set of states. Then to that I'm adding image Z, but I'm only adding it conditionally. Okay. If that image of I already has an I, okay, then I found a lasso. Okay. So I'm stopping at that. So the moment I find a lasso, I stop. Okay. So in that sense, I'm you know, computing those you know, all the kind of the lassos, you could say, all the states on lassos, you know, originating from you know, from I. Okay. And actually, I stop at the first lasso. Okay, is what what I do. Okay. So sometimes this is useful to, if you want to only look for certain states that are reachable through you know, kind of the shortest lasso up to a certain point. You can actually you know, do that. Okay. So but yeah, so these two, this you already saw. This was exactly what was used to characterize EG of some F. Okay. As greatest fixed point. You will see this is a little bit more complicated. I will get to that you know, later on. You know, this thing we will use it for doing model checking under fairness. Okay, it's a little bit more complicated here. Until now, I mean, all the taus that I've shown you are defined in terms of EX and AX. One step going to this. Here, for the first time, you see that a CTL operator itself is used inside a tau. And then if you're computing a fixed point over that, then you're moving into a kind of a different language. Okay, so you know, we'll get to that. This is something that it computes something, then there is no CTL equivalent of this thing. Okay, so you're moving into you know, mu calculus territory. Okay, so nonetheless, you know, we will get to that. So and you know, and so on. So this yeah, so I will, yeah, this I will get to a little bit later on. But what I want to now kind of, this is something that I already discussed. So this is kind of the structure, how your program, your CTL model checker will be actually when you implement it in terms of BDDs. So at the bottommost level, you will have something which implements the existential quantification elimination. For this, there might already be a function in the library for you. But what you will start by implementing is EX and AX. And then by looking at all the things you will be doing it. So you will by the way, every fixed point, CTL operator can be characterized, okay, as I've shown here, as a least fixed point of a tau, suitably defined tau, or a greatest fixed point of a suitably defined tau. When you have a G and R, it is usually convenient to be expressed as a greatest fixed point. Okay, so yeah, I specifically urge you, although I've already given you the book and given you a fixed point characterization, try and understand. We went through EU, AU, and EG. Okay, try and understand thoroughly AR and ER. Although they can be expressed in terms of negation of AU and EU, understanding this as a greatest fixed point would be quite instructive. Okay, that is something that I understand, and I will, so this, I'm just showing this table just to show you that every CTL operator can be expressed using it as implemented as a fixed point computation just by using EX and AX, and that's why you get this. Okay, so then you will have one implementation for each of the implementing for each of the CTL operator. They take a sub-formula, a BDD, that represents the set of states denoted by the sub-formula used in EG. In addition, all of them take the transition relation, okay? Because EG, EX, everything is assumes there is an implicit transition relation, which is also assumed to be as a BDD, and then returns a BDD, representation, a formula represented by a BDD, which exactly corresponds to the set of states that corresponding to EG. And then finally, you will have your model checker will take a Kripke model, T and I, that is transition relation and I, and a CTL formula which applies these things recursively down the hierarchy. This is what you will be implementing. Okay, this is your basic implementation, and you will be doing is you will be implementing a counter example generation component, as well as extending this to fairness. Okay, so but right now we can get started with this, with this basic implementation. Okay. So counter example. Before I show you the proof of, as you can see, these are not. Once you get a hang of it, maybe it becomes easy. But even if you do, trying to show that indeed these fixed points, computed using clean iteration of these functions, indeed those fixed points, least fixed points, or the greatest fixed points, they correspond to some, formula that in CTL, proving that will be would be instructive and to ensure that you understand it correctly, and then you are you're being honest. Okay, but before that, let me do counter example. Okay, what is a counter example of a CTL formula? So for universal operators such as AG, AF, and AX, a counterexample is a witness to the satisfaction of its negation. That is, a witness to its violation. Okay. So in a CTL formula, the universal operator, such a witness consists of a state and a path from that state that is a witness to its violation. Since you take the negation of that, okay, then it will be you should show that there exists a path that is violated. For existential operators, we just define, well, counterexample. I mean, it's not really a counterexample, but a witness to its satisfaction. Okay? Because for existentially quantified CTL operator, if you try to do give a witness to its violation, you'll have to show lots of paths. No, for every path you'll have to do it, and that's not practical. Therefore, this is how we define. Okay, since the negation of universal operators always can be expressed as an EG, or in terms of an existential operation. So the business of generating counterexample to CTL formula can be reduced to showing, generating witness to EG, EF, or EX, okay, of an existentially quantified thing. So you only need to consider how to generate a witness for EG and U. See, this can be done in general by saving intermediate results, which are formulas, during your fixed point computation, okay? And then kind of using that saved thing to trace it back. I will illustrate it for how you generate a witness for EU, okay? E F1 until F2. And I will raise certain questions to start thinking about generating witness for EG. And in the next class, by next class, I want you to give it some thought so that we can have a discussion. Okay. First, I will tell you how to generate it. So what I mean by storing all the intermediate results is, as you know, the fixed point computation using cleaning iteration for F1 until F2 starts with a tau 1 of F2, and then it computes a series of formulas representing sets of states from tau 2 until you reach a fixed point at the ith iteration that it adds to F2. That by adding mean it unions. So when I say you save something, what I mean is, suppose you save each tau 1, okay? So that part you compute. When do you have, so what you will have to show is that a witness is a state. Say you're given an initial state as well. From an initial state that satisfies that. But it can be just, so what is, what is that? So you really want your witness is something, when you reach your fixed point, you want to get a state in that fixed point and then extract a path originating from that leads you to F2. That is what is a witness to, what I call as witness to E F1 until F2. And you can see, conceptually, you can see if you had tau I minus 1 all the way to tau 1, and tau 0, of course, is false, here, because it's the least fixed point that you're computing. Okay. So if you have enough information to actually extract it, but the extraction itself is proceeds as follows. Okay, you really have to do a forward, what I call a symbolic simulation from a state in tau I, if indeed you want to show a witness for the arbitrary formula E F1 until F2, or if you want to pick a state that is also part of an initial state, you can start from something which is at the intersection, because so at the intersection of init and tau I. So what you have to, a counterexample is an actual witness. It is not a, so it is a sequence of states, okay? I mean, it is a state and a path. By path, I mean a sequence of states. I've kind of reversed the thing. So, yeah, maybe this is better to, no. Yeah, that's okay. So I've indexed this starting from S0. So S0 should be something that is a model. I mean, that satisfies tau I in it. It's a state. It's an explicit state that's, I mean, state that is in this. And there is something wrong here. Every Sj, oh, no, there is an extra Sj models here. So there should not be, there should only be one here. Remove this. Is such that Sj should be in the image, okay, of the previous the state Sj minus 1, and should also be in this top, so that to ensure that indeed it eventually leads to F2. This is what you'll have to do, okay? Since you have these BDDs, what you'll have to do is, what you really have to do is to write a program to actually do. And that you can do by saving all these BDDs corresponding to each of these tau i's in the iteration. And you do it, okay? So, yeah, is this clear? So, any questions here?
Sir, about the letters I and J, like do they, is there any dependence with the S0 and Sj for?
I have used, I think maybe it's a bit confusing here because I've named S0 as a state in tau I, okay? So, yeah, maybe there is a little bit of a problem, okay? No, I don't. No, I think I'm okay. So, no, there might be a problem. This was
I meant the tau, like tau I and this for Sj.
Yeah.
As tau J.
Okay. There are several typos here. Okay, one is it should be the superscript. Okay, I have used subscript. That is wrong. Okay, and if this I'm keeping it as Sj, then this should be S. This is correct. So Sj, the one that I pick here, should be in the image of Sj minus 1. Yeah. So this tau j. Okay. Yeah, this tau j might have to be kind of j. Since I've screwed up this subscript. I mean, so, just imagine, so you have to pick a state in tau I, okay? Where tau I is the ith iteration, okay? And then,
will it be something like I minus j?
Yeah, it should be I minus j, I think, something like that. Yes, yeah. Yes, I minus j, you're right, yes. Because I have taken the started from S0, it must be tau to the superscript of I is j plus 1 or something. Maybe I minus j. This is the previous, no, I minus j. So it should be I minus j, something like that. Yes. Yeah. So, and that's what you will have to, that you will have to do. So I'll fix this, yeah? And you kind of understand. So you'll have to, you have to pick a state in this fixed point, and then, pick a state in the image of that gets mapped, but it also happens to be in here. The reason you want to ensure that it happens to be in tau y minus 1 is because otherwise it may end up, I mean, you have to ensure that it is in the in the existential image. There exists one state into that, and the image, and then that it is a successor, and that it is inside this tau, because this tau is keeping track, ensuring that you have a successor state, in it, in here, that will eventually guarantee to lead to F2. Okay. So that's why, keeping that, saving that will be helpful, for you. So generating witness for EG of F. So EG of F, by, because here at least you have F2 as the thing, and you only need to consider the witness can be generated as a finite prefix leading into F2, into a state that is in F2. Okay, you don't need to have an infinite path as a witness for F1 until F2. But for EG of F, by nature, the witness has to be an infinite path. Okay. And as we said, the infinite path in a finite state system is always lasso shaped. And it has a finite prefix starting from some initial state and terminates in a state on a SCC. So the question is, how do you compute this? I mean, imagine that you used the greatest fixed point, that you computed it as a descending chain from true. The question that I'm raising is, how do you given the fixed point or additional information that you generate during your cleaning iteration, how you could generate this path, okay, this infinite path. Of course, since it's lasso shape that you're looking for, and there are only finitely many states, that is where, so I'm giving you a hint, okay? I mean, a fixed point tau I of true EG has EG, I'm sorry, this is EG of F, okay, not a subscript F. I mean, since it's lasso shaped, you'll have to look for lasso shaped path, and of course, it will eventually end up in your fixed point here will indeed have these strongly connected components. It'll end up there. So what you will have to do is, starting from your initial state, you have to look for a connected path that ends up in your a fixed point, okay, which is the which is not, yeah. You will have to start, so here all the intermediate result will not be of much help, okay, but you will have to start with the fixed point. In that, you will have to look for a state, okay, maybe you can, given an initial state, you can start from that, or you can pick some state. In that, you will have to look for a lasso-shaped path, a connected lasso-shaped path. Now the question is, I've given you a hint that the town that I showed you as an example that I claimed would generate a lasso-shaped path when it reaches its fixed point. Can it be used? Okay, is my question. If so, how you will use it? That's what I want you to think about. Okay, give it some thought, and we will discuss this in the next class. Okay, I promised you that I will end in 1 hour. I'm already gone. Therefore, I will defer. Showing you a proof of the equivalence between 3D fixed point characterization and the CTL semantics later on. So yeah, this is one. See, since this assignment is single, I mean, this programming assignment, I'm making it individual. The final project, I mean, you're only 3 people, so I don't mind you collaborating on on that. And by collaborating, if I had collaboration, you can discuss and so on, and since then you may be able to do something significant that will also be kind of satisfying, and something that I want to have you do for the first time that I've not done in my previous thing. What I'm really thinking of is for you to implement this procedure called IC3, okay, which is a very nice technique. It's an advanced model checking technique about a new thing. I mean, it is a well-known thing, okay? I mean, but it is fairly recent. Well, recent is about 15 years, okay? And it's been, but still the algorithm is mature. It's described in the book, and that will be an exercise in using a SAT solver for implementing a model checker, okay? And this is the first time I'm actually having it as a class student project, but I think it should be doable. And since I'm not planning to have any final exam, that is something that I want you to do. So, but this one, it will be individual programming assignment. You're free to discuss things amongst yourself, ask questions, and so on. But certainly, I want you to develop your own program to implement it. Yeah.
The final project, the 3 of us have to give one submission?
One submission. I mean, unless you don't want to do it individually. What do you want to do? We can talk about that. This is still, I mean, I have to define it in 2 weeks, okay? 2 weeks time, I will, yeah, I mean, you asked the question a little bit, there was some hesitation there.
No, I just asked, I didn't know if you meant separate submissions, but we can collaborate, or one submission for all.
No, I was actually, no, I think if you implement IC3, it's a significant project. So I was thinking of collaborating so that you will implement different components, okay? And I will, yeah, it's a single submission is what I had in mind.
Okay, yeah.
You have an issue with that?
No, I have no issue with that.
No, I meant all of you.
I don't have any
I'm
issue.
okay with the group thing.
Yeah, but I think what is, because then you have the thing of doing, see, but you will have to be honest, okay? And I trust you to be honest, okay? This is honor system, and we'll have to define it so that each of you will have some well-defined thing, and you carry your weight along. Only then it will work, okay? And I trust you guys there, based on my interaction so far that I've had. You seem quite dedicated, and my interaction that I'm getting, the feedback that I'm getting, the kind of questions that you ask are also kind of, you are, fairly good at grasping things. And I think that's what I have, so that then you can have an implementation of IC3. Yeah. But this one, I'm giving like 2 weeks time, okay? It's a bit aggressive, huh? So that's why I want you to get started on this thing as quickly as possible. Yeah.
Okay.
Just to confirm, you're talking about this.
This CTL thing is I'm assuming that I've already defined it, although I have not produced. I can give a return thing, okay? But I exactly want you to. I've already described these formulas. It takes you will have to implement. I mean, if you once you implement the least fixed point and greatest fixed point, you have it, okay? And counterexample and fairness. This is what I'm having to do. Yeah.
Okay.
So today is Friday. I'm thinking maybe 2 weeks from this Friday or the Monday following that is when I want you to have. Okay. Want to have the thing submitted to me. Yeah. Any questions?